Solvay process for sodium bicarbonate. Solvay process is used for manufacturing commercially sodium bicarbonate. Here we see first step in formation of desired product, sodium bicarbonate. The first step is formation of ammonium carbonate. That involves reaction of ammonia gas with water and bubbling CO2 through this ammonical solution. What we get is the product is ammonium carbonate. Next step involves further bubbling of this carbon dioxide through ammonium carbonate solution. This excess carbon dioxide converts ammonium carbonate into ammonium bicarbonate. Now, finally, sodium chloride solution is mixed with ammonium carbonate. Here, cation exchange reaction happens. Resultingly, we will get sodium bicarbonate and ammonium chloride. Here what we see, sodium bicarbonate having very low solubility in aqueous solution. What happens? It precipitates out, and what we'll get? Ammonium chloride as a waste product, and this reaction further drives the reaction. That's how we get our desired product from Solvay reaction. And the specification, as we know, according to Le principle, provide a driving force for more conversion of ammonium bicarbonate into sodium bicarbonate. Next, ammonium chloride is converted back into ammonia using lime or calcium oxide. Calcium chloride settles and ammonia gas we get, that is used again as a starting material for the formation of ammonium carbonate. This is how the first time that commercial manufacturing of sodium bicarbonate started. Next is colors of alkali metals. If you add alkali metal salt, sodium chloride, calcium chloride, or potassium chloride into these flames, what we are getting is, we are getting striking colors. The striking colors we observe on addition of alkali salts in flame is due to the excitation of outermost orbital electrons or valence electrons to higher energy levels. Let's see. We are adding a color and we are getting striking color. We are adding salts and getting striking colors. This is how it happens. Heat from a flame excites lower energy orbital electrons to higher energy orbital. Here comes the energy. It excites electron into higher energy orbital. But higher energy orbitals having a low stability what happens? This electron comes back and emits energy in form of visible light, because the energy there between higher energy orbital and lower energy orbital in case of alkalis is equivalent to visible light spectrum. When these electrons come back, we are getting a visible light as emission. That's what we get. Lithium uses cremation red, which is emitting light is around 670 nanometer. Sodium reduces around yellow spectrum, 589. Violet light comes from potassium, rubidium red violet, cesium almost blue. And these colors, what we observe, are not what absorbed, but what has been left behind. All the observed colors are complementary to those that are absorbed. Our spectrum is VQ, violet to red, energy of radiation reduces. So if we are getting a red spectrum, then light might be absorbed near violet end. In higher energy, radiation is absorbed. When we are getting blue energy, which is nothing but here blue, which is we are observing blue here, so energy absorbed will be around orange to reddish. In that region there somewhere light might be absorbed. So if you observe a spectrum which is having a lower energy, then absorbed energy will be higher. Sodium carbonate, which is also called a caustic soda. Carbonate part of sodium carbonate get hydrolyzed by water, and what we are getting on dissolution of carbonate anions a slightly alkaline solution. Why it is so? Because carbonate on hydrolyzing we are getting a bicarbonate anion called carbonic acid, which is weak acid, and what anion part here is called OH. It's called a strong base. As we already know, combination of a weak acid and strong base gives us an alkaline solution. Here we have sodium chloride, which is another salt of sodium. Most abundant resource or source for sodium chloride is seawater, which have around 2.7 to 2.9% by mass of different of these salts. Now you know commercially how it's obtained. You dry up the seawater. Left behind is sodium sulfates, sodium chloride, calcium sulfate, calcium chloride, magnesium chloride. Now for our consumption we are using sodium salt, sodium chloride, but having a lot of impurities as we saw here. All these sodium and calcium salts are impurity to sodium chloride. We need to purify for consumption. How will do? We make a saturated solution of sodium chloride known as brine and pass HCl gas through it. This is a saturated solution. We heat it up. What we left behind is sodium chloride, which is impure. We need to pass HCl gas of saturated solution of sodium chloride. This is how saturated solution is. We are passing HCl gas in that, and what we will get? Precipitation of pure sodium chloride according to Le Chatelier principle. If you remember, we are increasing the chloride, dissolved chloride anions in that. To compensate for it, pure sodium chloride precipitates out. Because calcium and magnesium chlorides are more soluble than sodium chloride, so they remain in solution. Next is alkaline earth metals. So far we have discussed about alkali metals. Alkaline earth metals and alkali metals resemble in many ways. So let's see. We having the first element of group 2 alkaline earth metals, beryllium, atomic number 4, magnesium, atomic number 12, calcium 20, strontium 38, barium 56, radium 88. Here, because we having 2 valence electrons in the alkaline earth metals, so we having 2 different ionization energies. First is for beryllium 899, second is 1757. Magnesium, the first ionization energy is considerably low, so do for the second ionization energy. Here, for all these elements, as we go down in group, ionization energy decreases down the group for both first ionization energy and second ionization energy. Here you see second ionization energy is higher than first ionization energy. The reason is how to justify the second high ionization energy. After the first ionization energy, what happens? It's a unipositive, so the effective nuclear charge for the valence electron, leftover valence electron, increases. Here if we have any magnesium, let's take an example of magnesium first. We ionizes the first electron, it's gone out. Now only a single electron is left, which experiences the same nuclear charge, which means now this electron handles all the charge left here. So it strongly binds to the nucleus compared to its original state. The effective nuclear charge increases. That makes second ionization energies higher. Now here we have hydration enthalpies just like we had for alkali metals, but here we see ionization or hydration enthalpies are higher because of higher charge to atomic radius ratios compared to alkali metals. Melting points we see fairly high, the decreases down the group. But here you see abnormally. Magnesium, we know these are due to atomic sizes. As you go down a group, atomic sizes increases. You see melting points of a bit higher for bit lower for magnesium compared to calcium. We expect it to consistently reduce, but that's not the case. So you see hydration enthalpy reduces as we go down the group, and the metallic radii is also increases down the group. Same charge to radius ratio is the reason for reduction in hydration enthalpy of group 2 metals. As we move down the group, charge remains the same, but radii increases, which reduces charge to radii ratio. The capacity to hydrate molecules in aqueous solution depends upon charge to radius ratio only. That is the reason we saw reduction in hydration enthalpy as we move down the group. Again, just like alkali metals, here we see same striking colors in flames for alkaline earth metals. Concept is same. Excitation is from lower energy states to higher energy states on exposure to heat. That's what we see, striking colors. Heat from the flame excites lower energy orbital electrons from alkaline earth metals to higher energy states. These electrons de-excites to give us emission. But we already know observed colors are complementary to what has been absorbed. But what you see, first two elements, beryllium and magnesium, do not have visible light spectrum or visible light colors emitted on exposure of these salts to flame. The reason is the energy difference between the two states of beryllium and magnesium are higher than what is the band gap of visible light. While for calcium, beryllium and strontium, these band gaps or the energy, excitation energy is equivalent or lies within visible spectrum. For calcium we get red, meaning this absorption is near somewhere violet to indigo. Same thing goes to the strontium, crimson red, and barium having green color. So its absorption will be of bit lower energy than calcium. That's what we see with blue. This is a spectrum. If the color observed is red, absorbed will be somewhere here, blue to violet. If observed color is green, absorption will be somewhere yellow-orange in that reason. So if we observe this higher color, absorption will be of lower energy. If we observe lower energy color, absorption will be from higher end. As we just already discussed, beryllium and magnesium do not give color in flame, simply because excitation energy higher than visible spectrum. They do not react directly with oxygen and water. But if we finally divide the magnesium, it reacts with air to form magnesium oxide and nitrates. This happens just like lithium. Beryllium combines with hydrogen to form dihydrides. The beryllium dihydride. What happens? Beryllium hydride we are preparing on reacting beryllium dichloride with lithium aluminum hydride.